The assignment that is due today is 1.5. 1.5 is, the main idea is independence. I'll call it independent events. Independent events. We actually talked about this our first day of probability when we did 1.1. We know whether two events are independent when the first event does not change the second event, right? This is something we've talked about before. Independent events, I don't like that E. Independent events are events where the probability of the first event does not change the probability of the second event. So independent events are events where the outcome of the first event, the outcome of the first event, I'll use F, I'll just use, instead of spelling it out, first event does not change the probability of the second event. I'll use, instead of spelling out, second event. When you flip a coin, the second coin doesn't know what the first coin was. They're not related. If I flip a coin and I get heads the first time, I'm about to flip the coin the second time. The probability that the second coin is going to be heads is the same. It's still 50%. So my wife and I, we drove out to Area 51. The area, you can't go to Area 51, you'll get shot. But outside of Area 51, the closest you can come to Area 51 where it's still safe, there along the freeway, or maybe it's a highway, there is a restaurant / store where you can buy souvenirs, and there's a big, sign out front about aliens, and there's a lot of merchandise that talk about Area 51, and I love the idea of ghosts. I love the idea of aliens, but I don't really believe that aliens have come to Earth, and I don't believe that ghosts are real. But I would love to believe. I love going on ghost tours. I love going out to, say, like Area 51. I would love to go to Roswell. I think that would be cool too. But I don't believe. I want to believe. But I just don't feel like there's enough evidence to say yes, it's true. So, anyway, on the way back from that area, we dropped by and got some souvenirs, and on the way back we stopped by Virgin River, which is a casino, and we gambled a little bit. Now, I've said this in this class before, and I'm going to say it again. In the state of Utah, it is illegal to gamble. In Nevada, you can gamble, but how old do you have to be to gamble in Nevada? You have to be 21. And I've also said in class, if you gamble, do not expect to make money gambling. If you do make money, awesome. If you don't make money, you shouldn't be upset about it, because you should be playing with money that it's okay to lose. Gambling should be seen as a source of entertainment, not a source of income. I'm going to say that again. It's so important. Gambling should be seen as a source of entertainment and not a source of income. If you think you're going out to Mesquite or Vegas or what's the other big one? Wendover. If you think you're going there to make money, then you are most likely going to leave being disappointed. Gambling is a source of entertainment, not a source of income. So I was sitting at the blackjack table, and the idea of blackjack table is you're trying to get 21 without going over 21. And you're also trying to get a score that's higher, that's better than the dealer. And if you get a score higher than the dealer without going over 21, then you win. If I put $5 there, then I get $5. I get to keep my $5 plus I get another $5. If the dealer wins, then he takes $5. So my wife lost $40 and I lost $20, but that was okay. It was just a matter, the whole time we were out there, it was just a source of entertainment, not a source of income. So it was okay that we lost. But I was sitting next to a guy that we had lost a couple of times in a row, and he said, "Oh, I'm feeling it. I think we're due a win. We're due a win." And he like doubled his bet. Is a gambler ever due a win? You're not due a win. The cards don't know what the dealer had the previous time. These are independent events. So let's look at, and we know here is our equation for independent events. The equation for independent events, we know that they're independent events. The equation is, if I have the probability of getting event A and event B is the probability of event A times the probability of event B. That's our equation. Isn't that what we learned about flipping coins? If I flip a coin, the probability of getting heads. Don't I look at the events separately and then I multiply? Does this equation make sense with everything we've learned so far? If I flip a coin, what's the probability of getting heads and heads? We look at these separately. What's the probability of flipping a coin and getting heads? 1/2. Now let's look at the second coin that doesn't know what the first outcome of the first coin was. I'm about to flip the second coin. What's the probability I'm going to get heads? It's also 1/2. So together, we just multiply these. So the probability of event A happening and event B happening, in this case, it's heads, is 1/4. That should be consistent with everything that we've learned so far. This should not be considered new math. Okay, we're good? Is everybody still copying? Okay, I'm going to move on. All right, I'm going to do, what kind of chart is this? What's that called? Yeah, it's either a two-way table is fine or a two-way frequency table. Either is fine. Weekday versus weekend and total. Let's move Chai over. This is called a two-way frequency table, or a two-way table is fine. I'm going to fill in a bunch of values in here. How about, let's say that this is 65 and this is 107. This is 195 and this is 339. Now here's the prompt. We're going to say that this is data collected regarding a restaurant. The restaurant primarily serves chicken and fish, and they sell chicken and fish. They have the restaurant open on the weekdays, and they also have the restaurant open on the weekend. And so How many people went to, if this two-way table represents all of the customers for a week, how many people went to the restaurant during the week? Yeah, it should be, here's the total number of individuals who went to the restaurant, should be 339 customers that went to the restaurant. And then what does this represent here? What does that mean? This 107, what does that mean? Yeah, people, customers that ordered fish on a weekend. That's what that means, people who got fish on a weekend. Can I figure everything else here? All right, how do I figure out what goes here? Yeah, so we're going to take this number here and we're going to subtract the 195 because the total should be the top number plus the next number gives me the third number. So going backwards, if addition gives you the score forward or the value forward, then we subtract going backward. That's really a cool thing about, it's called inverses. Those are called inverses. It's a really cool idea that if I have something plus 195 equals 339, then I'm going to subtract going backward. And so that's going to give me 144. Is that right? If I go backward, 144. So that this 144 plus 195 gives us this 339. Yeah. So I can just get rid of all that. That was just our example. That's a really cool idea in math that going backward is an inverse. So this would give me, this is 144. Is it possible to figure out what goes here? How? Yeah, we subtract the 65. So again, we're trying to think of something plus something gives us this. So going backward, we use the inverse, which would be minus. And so we're going to subtract going backward. And what I'm getting going backward is 79. Is it possible to figure out what goes here? How? Yeah, we're not going backward, we're going forward here. And so if I'm trying to find the total means plus, right? In mathematics, total means plus. It means we're taking, if I talk about any type of total, what's the total amount of money that you have? You have to add up your piggy bank. You have to add up what's in your bank account. You have to add up maybe that your brother owes you $5. That would be you adding it up. Total means plus. Sum also means plus. So I'm adding those up and I'm getting 186. What about, is it possible to figure out what goes here? Or do I not have enough information? What do you think, Sophie? Yeah, so don't look at the column, look at the row. If I look at the row, then we're just missing one value. So we're going backward. We will use subtraction. So if he's correct, we're just going to subtract the 107. We're going to subtract this from the 195. And then that's going to give me 88. All right, is it possible to figure out what goes here? There should be, you should recognize two different ways. We can either add that or we can subtract this, right? To get that. Yep, either way is acceptable. In fact, you should do both. Why should you do both? Yeah, to double check. If you get the wrong answer, what does it mean? If I add these and I get a number here, and then I subtract these and I get a different number here, what does that mean? Yeah, I did something wrong. So go back and erase your stuff and start over. That's a great way of checking your work. All right, so what I'm getting is, let me change this back to red. And I'm getting 153. Looking at this chart, when does the business get when does this restaurant get the most business? When does the restaurant get the most business? I heard somebody back there. Was that Cohen? Oh, was that? It was Reese? Reese, good job. Yeah, it's the weekends. We just look at these. We compare. What we're doing is we're comparing the weekday with the weekends. Is that logical? That, I mean, the weekdays we have 5 days. We have Monday, Tuesday, Wednesday, Thursday, Friday, and then the weekends we only have Saturday and Sunday. Is that logical that in 2 days we're going to have more customers than 5 days? Is that logical? Can we wrap our heads around why that might be? Any guesses why it's possible that you might have more customers on the weekend on 2 days, just Saturday and Sunday, than on 5 days, Monday, Tuesday, Wednesday, Thursday, Friday? Is that even logical? Can we wrap our heads around why that might be? Yes. So we don't even have enough information. There might be, it might not even be open in the morning on the weekdays, and then on the weekends it's open longer. Okay, so we don't know the hours, so that would be a variable that we don't know that could contribute to why the weekdays and the weekends or why the weekends have more customers. I think that people have more time on the weekends to even go out to eat. I notice, and I'm not saying that, my wife and I are certainly, we don't represent the entire population, but I notice that my wife and I, we go out to eat more often on the weekends than during the weekdays. Just because we're both working on the weekdays, and it's easier just to, it's, if we're going to have sit down and enjoy ourselves, it's easier to do on the weekend than the weekdays. Morning, Olivia. So that might be one reason. And I think that, people who, if you do dine out, a lot of times, oh, thank you. I mean, yeah, on the weekdays, if you do get food, it's usually fast food. It's like, oh, I don't want to cook, so I'm just going to quickly stop by McDonald's or whatever and pick something up. But usually sit down restaurants, usually on the weekends, sit down restaurants have more business. It's not always true. I know that like El Chihuahua, for example, has a special on Tuesdays. They have this Ducky Death Star kind of special, and people tend to go there because it's cheaper on Tuesdays than other days. And so they're really crowded on Tuesdays, but it was because of their special. So, and I think that, I don't know if you guys like Papa Murphy's. I think Papa Murphy's is awesome. It just tastes like really healthy pizza as opposed to maybe greasy or something else. But Papa Murphy's has a Tuesday special as well. And so they tend to be more crowded because of that you can get pizzas for cheaper at Papa Murphy's on Tuesday. So there are some variables that could change this, that would make weekends more profitable for the company than on the weekdays. So let's go ahead and we'll just say here, based upon the data, again, there's not enough evidence of why, but there are some variables we can consider, that the weekends are more busy. So I'm going to just write weekends. Weekends. When is the percent of fish sold the greatest? When is the percent of fish sold the greatest? Let me zoom out and write this question down. So when is the percent of fish sold the greatest? And I heard somebody say the weekends. Okay, so I hear somebody say the weekends. Can we confirm that that's true? Anybody want to second that? Do we agree or disagree with this claim? Agree? So how do we get it? How do we get that as the weekends? Is the question asking which day do we sell the most fish? Or does this word here change things? Am I asking which day do I sell the most fish? Or does this word change things? It changes things because I'm not looking at the number of fish sold. I'm looking at what? The percent of fish sold. So that sort of changes things. In fact, I'm a little bit suspicious that we might not be right about this. So I'm going to just erase it for now, just in case. And so we're looking at percent. How do I figure out the percent? This is the percent of fish sold. So I want a percent of fish sold on percent of fish sold on the weekend. The notation for this, I already know it's going to be a weekend. It sounds like conditional probability. Would you agree that this sounds like conditional probability? If I'm talking about the percent of fish sold on the weekend, isn't that conditional probability? What's the notation for conditional probability? Isn't it this? So the probability of fish given that it's a weekend. How do we do? So here's my ledger. F is fish. C is chicken. What word? Weekday and weekend, they both start with a W. How do we decipher the difference? What should our ledger say? Okay, day is for weekday. I think that's a good idea. Weekday and weekend. Okay, E weekend. Okay, weekend. I think that's a good idea. Weekend. All right, so we have the probability of fish given that it's a, what did I say, weekday or weekend? Actually, we have to figure out both. So we have to do both. We're trying to figure out both of these. Fish and let's see which one's greater. That too small? Can you guys still read that or is it too small? I just want to be able to see the numbers. So how do I write the probability for this? The probability of fish given that it's a weekday. What's my equation? Which is actually that would be this, right? Okay, so you have so fish is 79 over 144. Yeah, does that make sense? So this is conditional probability. This is the probability of getting fish on a weekday. So the answer would be 79 over 144. 79 over 144. And when I throw that in my calculator, I'm getting about 55%. What about the next one? What's my equation for the next one? Fish given weekend. Fish given weekend. Right? That's 107 over what? 195. 107 over 195. 107 over 195. And when I throw that in my calculator, I'm getting something very close again. I'm getting 55%. Huh. What does that mean? Yeah, it's about the same. Yeah, for weekends or weekdays, it's about the same. So when is the percent of fish sold greater? It's the same for both. We're getting about the same, the percentage is the same. So the frequency, when my customers come in, it looks like the frequency of buying fish on a weekday and a weekend are the same. They look the same. They look the same. All right, I want to talk about this idea. Let's go ahead and grab our equation. And I want to know, let's use our equation. The equation is the probability, we know whether the events are independent or not by our equation of the probability of A times the probability of B equals the probability of A and B. That would mean that they are independent. So I want to know, that's my next question. Is chicken sold independent of the day of the week? Is chicken sold independent of a weekend or independent of the day of the week? Is chicken sold independent? That's my next question. Is chicken sold independent? Is that too close? That's way too close. All right. It's just easier for me to write when it's bigger. My question is chicken sold independent of a weekday? Is chicken sold independent of a weekday? Well, we have to use our equation. This is independence. Use our equation of the probability of A and B. Does it equal the probability of A times the probability, the probability of B? What does this mean here? Let's put that in context to chicken sold on a weekday. How do I write this equation? This probability of A and B. What does that mean in the context of the problem here? Yeah, chicken and weekday. Does that equal what? What's the probability of A? Okay, probability of chicken times what? Probability of the weekday. Yeah, we have to see whether these equations, whether this is true. That will answer whether we have independence or not. What if this does not equal? Then it's not independent. Yep, it's dependent. If it does equal, then it's independent. Okay, let's go ahead and try to figure this out. So I'm going to go back, I'm going to zoom out. It's harder for us to see. So I'm trying to find the probability of chicken and the weekday. What would be chicken? The probability of chicken and the weekday. What would be my fraction? Remember, probability is always the number of ways it can happen out of the total number of outcomes. The probability of chicken and a weekday. What's my fraction? Probability of chicken and a weekday. So you said it was 65, right? That's a chicken and a weekday, I agree. So the number of ways it can happen out of the total number of outcomes. What is the total number of outcomes? $144. 144, this one here? Yeah. Then that would be conditional. Is this a conditional statement, conditional probability? Or are these conditional? The 153 over here? That's still conditional. When you limit the denominator, because it's conditional, you're looking at a specific group of people. 339. Yeah, we're looking at the number of ways it can happen out of the total number of outcomes, out of the total number of outcomes. The total number only changes if it's conditional probability. So this is 60, and we're looking at 65 out of 339. 65 out of 339. I'm going to zoom in. This is going to be 65 out of 339. And what's the probability of chicken? We're looking at the probability of chicken. Let's go back up, look at our chart. What's the probability of chicken? 153, that's the number of ways it can happen. That's the total chicken, 153. Out of what? Out of 339, yeah. Number of ways it can happen out of the total number of outcomes. 153 out of 339. $153 out of 339 times the probability of, what does this mean again? The weekday. Yeah, that's the probability of a weekday. What's the probability of a weekday? Yeah, so here's weekday. Here's the number of ways it can happen out of the total number of outcomes. Yeah, again, 339. Unless it's conditional probability, the denominator should be the total number of outcomes. And so this is going to be 144 out of 339. 144 out of 339. 144 out of 339. Now the question is, do these equal? If they do equal, then they're independent, which means it doesn't matter if it's a weekday or a weekend, that people are just as likely to order chicken as fish. That's what that means. If we get the same number on both sides, it means that the probability of ordering chicken is the same, whether it's a weekday or the weekend. So I'm going to throw this into my calculator, and I'm going to get something. So this first one gives me 0.19174. And when I throw this in my calculator, 191, I'm getting 0.191714. Are these equal? No, back here it looks like they're not equal, but they're pretty darn close. And so because they're darn close, we're going to round it to that they are equal. They're approximately the same. About 18, here we have about 19% chance that of somebody ordering chicken on a weekday. Here we have 19% of somebody ordering chicken and times the probability of somebody ordering chicken or ordering on a weekday. So we have something that's super, super close. So we're going to say that they are close enough. We're going to say that they're close enough. And we're going to say that they are independent. Independent. Now, what does it mean to be close enough? Well, part of that is a personal judgment. You have to look at those numbers and you have to decide on how close those, if these numbers were something like this, one of them is say 23% and the other one is 18%. I'd say that's different enough that we would say that they are not independent, that they are dependent. But these ones are super close. So we could round it. to 20 or 19% for both of them. So we would round them to and say that they're independent. Now, in comparison, let's look at our example that we used in the past on the Titanic. Let's see if I can find the Titanic fast. I don't know how fast I can find the Titanic, but let's see if I can. I know that they're in. The Titanic is going to be on my C drive under my user. And we'll go into OneDrive and this year and secondary math 2. And let's go to notes. When did we do the Titanic? Was it last time that we did the Titanic, or was it the time before? It was last time? Okay, so it should be right in here. Okay. Oh, there they are. Awesome. Okay, I want to know, I'm actually just going to borrow this. I'm going to borrow these numbers here for last time. Copy, and I'm going to paste it into my notes. Now we're going to do the same thing. I want to know whether being male and surviving, whether those are independent. I want to know whether male and surviving, whether those are independent. So was surviving independent of gender? That's really the question, right? Was surviving independent of gender? Yes. Was surviving on the Titanic independent of gender? So we're going to ask, let's be more specific. If being was male and surviving, or were male and surviving independent? Were male and surviving independent? So what's our equation then? What was our equation? The equation is the probability of A equal, the probability of A and B equals what? What was our equation? Yeah. In the context of males and surviving, what is the first piece here? What does that mean? Let's try to connect it to the context. And so the first one, probability of male, A and B is the probability of male and survive. Okay. Equals what? Yep, I've survived. All right, looking at our two-way table here, what is the probability of male and survive? Okay, we have male and survive is 146. It's always, probability is always the number of ways it can happen out of the total number of outcomes. So we have the number of ways it can happen is 146 out of the total number of outcomes. Yep, it's not conditional probability, so we have to go with the total number. It's not conditional probability, so we have to go with the total number. So that's going to be, this is our 146 out of this 1207 equals, what's the probability of male? Okay, probability of male, we're looking at all the total of males, 805 out of the total number of outcomes. Yeah, 1207. So we have 805 out of 1207. What's the probability of survives? Yeah, so here's survives. Here's the total number of survives. of 442. 442 out of the total number of outcomes? 1207. Now the question is this equal? What do you think? Is it going to be equal or not? Any guesses? Just not sure? Well, take out my calculator. I have 146 divided by 1207, and I'm getting something like this. I'm going to use a different color. Just use blue. I'm getting 0.12096,106, something like that. So the probability of male and survives is about 12%. Probability of males and survives. So if I randomly select from the group, what's the probability I randomly select a male that did survive? That would be about 12%. Okay, does that equal this other one? So 805, so that's 805 divided by 1207. I'm getting so 0.666948 times 442 divided by 1207 gives me 0.366197. So here's the probability of surviving on the Titanic, not just ignoring gender. Here's the probability of being male on the Titanic. And the question is, are these independent, surviving and being male? So I'm going to multiply these together times this other number, and I'm getting 0.244232589. These are not equal. Because they are not equal, you can see that the spread between the two numbers is great enough that we would say that they are not independent. They are dependent. And that makes sense because what was the maritime law? Who goes first in the lifeboats? Women and children first. So that makes sense that surviving on the Titanic was not independent of gender. It was your chances of surviving were very dependent on gender. So anyway, I showed one example of chicken and weekends that we did have something that these were really, really close, indicating that chicken and weekdays or chicken and weekends, that those are independent. The chances of ordering chicken on a weekday versus a weekend are about the same. Here, the chances of you surviving if you are male is not the same as the chances of surviving and female. So we saw some examples of dependent versus independent. Okay, moving on. I'm actually going to just go to the top. Do I have anybody that's still writing? I don't want to zoom on and do something else if somebody is still writing. Yes, sir. Yes, sir. Raymond, you can go to the bathroom. If you miss something, you'll have to go back and watch the video though. I never want to say to a student, you can't use the bathroom. I think the worst I would say, if I have students that take advantage and go to the bathroom and then they come back 20 minutes later or something, I think the worst I would do is say, well, you were gone so long, I'm going to mark you absent. But I think that as long as you're not taking advantage, there's no reason to say you can't go to the bathroom. In fact, I'm concerned about, because there's all sorts of issues people have, and I never want to limit that. So we used to have something where you could go to the bathroom like twice a term or something like that. I don't want to limit you. But I do want to warn you, if you're gone a lot, you're probably missing class a lot, which means if you learn everything through repetition, you're not getting any repetition. So that would definitely be something that would probably count against your grade inadvertently, not being in class. So I really want to use this equation. I really want to focus on this idea of the equation for independence. So one more time, the equation for independence. I need to zoom in. It looks like the equation for independence is the probability of A and B equals the probability of A times the probability of B. That is for independence. Now I want to compare this to another equation that we have. Independence. Now there's another equation that we talked about for being mutually exclusive. What does it mean if we're talking about two events in probability that are mutually exclusive? What does that mean? There's no intersection. Yep. Mutually exclusive. Exclusive means no intersection. So the equation is, the equation is, let's consider something. Let's look at something. Let's look at two different events. This is event A. This is event B. This is event X, and this is event Y. So we have four different events. Now, we have these boxes around the events called the universal set. So that would represent the whole entire sample that I was studying for each one of them. So they're separate. Which of these is mutually exclusive? Is that, would that be events A and B or events X and Y? A and B are mutually exclusive because there's no intersection. You can be part of A, but you can't be, if you're part of A, you can't be part of B. If you're part of B, you can't be grouped in the other group. And some examples are being, surviving or not surviving. There's not a middle ground there, unless you're talking about something fictional like Walking Dead. Otherwise, you survive or you don't survive it. There's not a middle ground. You can be pregnant or not pregnant. That would also be something that would be mutually exclusive. Or going left or right, but you can't do both. That would be something else that would be mutually exclusive. Flipping a coin and getting heads or tails. If you flip one coin, you can get heads or tails. You can't get both. So we'd have mutually exclusive. So what does it mean? Looking at this, looking at this example, what do you think the probability of A or B, what that would be? What would my equation be for the probability of A or B? Which is already different than independence, right? Our equation for independence is the probability of A and B is A times the probability of A times the probability of B. But looking at this, just think logically. Let's just think logically. Let's look at this image here. What makes sense when you look at this image? If I want to know the probability of A, the probability of A or B, trying to get something in here or here. If you think logically, what would make sense for what our equation would be for that? Anybody have any ideas? Just thinking logically. Grace, any ideas? What seems like a logical way of saying that you can be part of this group or this group? Well, if it was the probability of A given B, then the answer would be actually the probability of A given B. That means I take all of this. Yeah, I mean, they're not related. I think you're thinking of an intersection where you're looking at something. So this can't be conditional, because if I limit one, then the other is 100%, right? If I say given A, what's the probability of A? That's 100%, ignoring one of them. So any other ways of trying to figure out the probability of E? So I just want to know, we're going to take an individual, where some of us are in this group, some of us are in this group, and I want to know the probability that of A or B. Is that Abrielle? Yes. Anybody? Let's think about that. Probability of A or B. Anybody have any ideas? Sophia, do you have any suggestions? How would I calculate the probability that somebody's in this group or they're in this group? Let's say that this represents turning left. No, wrong tool. This one is the probability of turning left. This one's the probability of turning right. What does it mean to be on the outside then? Yeah, going straight or stopping and not going at all, right? And so if I wanted to know the probability, I'm standing on a corner and I'm watching cars go. And all of the cars that turn left go in here, all the cars that go right go here, and all the cars that do neither go there. And then I want to know the probability of turning left or turning right. Isaac, any ideas? Doesn't it make logical sense that we would take the probability of left plus the probability of right? Let's do an example. What if I have something like, let's say that left is, I don't know, there's, 25% of the cars turn left, and say 30% of the cars turn right. So what would that be left that do neither? Well, if I have 20% and 30%, that gives me 55. So wouldn't this be 45? So what's the probability of turning left or turning right? Yeah, we just add them. We just add them. We just take this 25% and the 30%, that gives us 55%. That would turn left or right. Does that make sense, or is it confusing? I am looking for an equation. Yeah, here's my equation. And I was looking for an equation. This was the equation. The probability of A plus the probability of B. Oh, is this it? Are these in our notes at all? I don't know if this one's in our notes. It is? It is? Okay. Why doesn't this work for when we have an intersection? Why is this not true? Yeah. So what would it mean if this is, say, let's say that this is, let's say that this is, oops. Let's say that this is 30% and this is 25% and this is 10%. That'd be 3, 4, 5, 65. That would be 35 out here, 35. So if I took the probability, so the probability of A, probability X or probability of X or Y, does that equal the probability of X plus the probability of Y? What's the problem with that? Probability of X is this value here, correct? Okay, and so that would be 40%. Oh shoot. Plus the probability of Y, which would be this value here, which would be 35%. So together, the probability of X and Y would be 4, 5, 6, 7, 75%. Does that sound right? There's something I did wrong here. If I take the probability of X, which is here, and then plus the probability of Y, which is here, what's the problem? I'm counting the middle twice. So that's the problem. When you have an intersection, you're counting the middle twice. So our equation then would be, we would have to subtract the middle. We would have to subtract. What's the formula for, or how do I write the middle? Probability of what? Yeah, X and Y. Yep. So that's the equation if we have an intersection. Our equation so there we have a couple of equations, right? Let's look at them. We have our equation for independence. For our equation for independence, if I want the probability of A and B, what's our equation? The equation for A and B, Sophia, is what? Probability of A times the probability of B. That's our equation. For independence, that's our equation. The probability of A and B, the equation for independence is the probability of A times the probability of B. Cohen, what is the probability of mutually exclusive? Probability of A or B is what?
Oh, it's a probability of A plus probability of B.
Nice. It's probability of A plus the probability of B. That's for mutually exclusive. What is Isaac? What's the probability if I have an intersection? If I have an intersection, what's the probability of X or Y?
X plus 5.
So the probability of X plus the probability of Y. If I have an intersection, minus the probability of what? How do I read this, Isaac? Probability of what? What's that symbol, Isaac, that goes like this, an upside down U? Doesn't it sort of look like an A for and? Yeah. So that would be, so it's the probability of X. Isaac?
X and
Probability of X or Y is the probability of X plus the probability of Y minus the probability of X and Y. Isaac, why do we have to subtract the probability of X and Y? We don't want to count it twice. Yep, that's absolutely true. We don't want to count it twice. If I take the probability of X, which is right here, plus the probability of Y, which is right here, that's going to count the middle twice. So that's why I subtract it. Isaac, why don't I have to subtract this when we have when something is mutually exclusive?
well, it's not being counted twice and it's not in it.
Yeah, There's no intersection, so we're not counting it twice. Yep. Are events that are mutually exclusive the same as independence? If something is mutually exclusive, is that the same as independent? No, they're not the same. Mutually exclusive means you can be in one group, but not in the other group. Independence, can you be part of the same group with independence? Yeah, we can have survives and male. Survives and male, well, that was an example that wasn't independent. But our example of chicken in the weekends, you can be in both groups to still show independence of chicken is independent of the weekends. So yeah, all right, so I have some examples and this is sort of what you're going to see on your homework. And what I want to do is I want to prove, so I want to know, so this is your prompt here. Here are the directions. Dependent or independent? Our first example. I'm going to flip I'm going to write this down. So I have the probability of heads. I'm going to flip a coin twice. Probability of heads is 1/2. Probability of heads a second time is 1/2. I'm trying to figure out the probability of heads, or is that or? What is it? And so the probability of heads and heads is, what would that be, 1/4? Is this an example of dependent or independent? Independent. How do I prove it? Yep. So we can explain it that flipping a coin doesn't affect the other, but can we prove it mathematically? We're going to prove it mathematically by using our equation of the probability of A and B has to be what? What's our equation? Yeah, multiplied by the probability of B. Yep. So is this equal to this times this? Yeah, let's show it. We have 1/4 equals 1/2 times 1/2. And what's 1/2 times 1/2? 1/4. So I have 1/4 equals 1/4. So independent. Independent. We have events that are independent. Okay, let's do another one. Move over a little bit. Here's our next example. Did I just number it number 1? Yeah, so here's number 2. Number 2, probability of A is 1/10. The probability of B is 3/8. And the probability of A and B is 1/20. Same directions, dependent or independent. Same directions, dependent or independent. How do I prove it? What's our equation? Yep, absolutely. So the probability of A and B is equal to the probability of A times the probability of B. If this is true, they are independent. So I'll just plug in values and see if this is true. Is it true that 1/20 is equal to 1/10 times 3/8? Is that true or not? It's not true. Yeah. So if we plug in the, yeah, so this is going to give us 1/20th. Is that equal to what's this? 3 what? 3/80. Can that be simplified? No. So are these equal? No. So dependent. So dependent. Let's do another one. Number 3. Probability of A equals 3/4. Probability of A or and B equals 1/8. And the probability of B equals 1/6. Are events A and B independent or dependent? And Olivia's on her phone. Thank you. Reese, what do you think? So the directions for these problems right now is that I want to find out whether these events are dependent or independent. And we did a couple of examples already where we looked at, a restaurant that serves chicken and fish, right? And they serve fish and chicken on weekdays versus weekends. And we wanted to see whether whether chicken on the weekdays, whether that was independent. In other words, does it really matter if it's a weekday or a weekend when chicken is sold? And it turns out that they are independent. And so, in fact, we found that these numbers are super, super close. And so, yeah, we're looking at, it doesn't matter if it's a weekday or a weekend. The probability that somebody's going to buy chicken is the same. Now, we also looked at the Titanic, and I was curious to calculate whether being male and surviving on the Titanic were independent. And what did we find, Reese? That surviving and male, did we find that that was dependent or independent? That is independent of gender to survive on the Titanic? Did we find that these numbers are really different? That the probability of A and B equals the probability of A times the probability of B?
Oh, so yeah,
It's dependent, right? Your chances of surviving on the Titanic were very dependent on your gender, Reese. Does that make sense? Do you know the story of the Titanic? Why was it dependent? Yeah, women and children first. So your chances of surviving the Titanic if you were male, your chances of surviving was less. So now I'm just giving you a bunch of numbers and I want you to tell. So then we went over some equations, right? The equation for independence, and then we talked about the equation for mutually exclusive versus any of the other equations. So these are just some important equations in probability that help us prove different situations. So we did one here on flipping a coin, and we found that we have independence, because the probability of A and B, it does equal the probability of A times the probability of B. Now I'm giving another situation here, and we found that the probability of A and B does not equal the probability of A times the probability of B. So they are dependent. And so, Reese, my question then is, this situation here, are events A and B dependent or independent?
it would be, so if A times B.
Okay, so wait. If event A times event B, or the probability of event A times the probability of event B equals what?
They aren't equal to that third number.
Oh, the probability of A and B. If they're not equal, what does that mean?
I know, dude.
They're dependent. If they're not equal, they are dependent. If they are equal, then they're independent. How do we prove this? Reese, how do I prove this?
Because if you multiply 3/4 and 1/6, you don't get it.
Okay, let's try it. So we have 3/4 times 1/6, and I want to know whether that equals 1/8. Well, 3/4 times 1/6 is what?
Is 3/24.
3/24.
And then it gives 1.
Yeah, that can, in fact, this is a really cool rule that we can know that they are divisible by 3. How do you know when you look at a number, how do you know it's divisible by 2? If I look at a number like this, how do I know if it's divisible by 2? It's an even number. The way I know it's, do you know the rule to know whether it's divisible by 3? You add the digits. That's a crazy rule. You just add the digits. 1 plus 2, I'm adding the digits. I get 3. If the new number, the sum of the digits, is divisible by 3, then the entire number is divisible by 3. If I add these digits, what do I get? 6. Is 6 divisible by 3? Then 24 is also divisible by 3. So that's sort of a cool rule that works. All right, so 3 goes into both, and 3 goes into 3 one time, and 3 goes into 24 8 times. So Reese, I do get the same thing. Reese, which means what? They're independent. These are independent. What is your homework for tonight? 1.5.